Welcome to this second video tutorial on refractometry. In the first video, we focused on the use of a refractometer, specifically a PTR46, to measure the ORI of an ethanol water solution in order to measure the ethanol concentration. We demonstrated the correct procedure for ORI measurement and also how to use a calibration curve to relate sample ORI to sample composition. In this video, we'll look in more detail at the construction and application of the calibration curve for the ethanol water system. We'll see that the relationship between ORI and ethanol concentration is linear only across a limited range of ethanol concentration. We'll look at the relationship across the full concentration range and consider how to handle the nonlinearity. Let's start by looking at the calibration curve for the ethanol water mixture, which we already used in the first video tutorial. Please note that this relationship is valid only at a temperature of 25 degrees C. If for any reason ORI is to be measured at a different temperature, then a new temperature-specific calibration curve will be required. Additionally, the relationship is valid for ethanol mass fractions in the range 0 to 0.3. So how can we use this calibration curve to analyse more concentrated ethanol solutions? To experimentally characterise the relationship between ORI and ethanol mass fraction, we first prepared a series of ethanol water solutions across the full composition range from pure water to pure ethanol, as shown in this table, with a total mass of 10 grams in each sample. Please note that the ethanol concentration is specified in terms of mass fraction. For distillation calculations, for example, it may be easily converted to mole fractions. The next step towards constructing the calibration curve is to measure the ORI of samples of each solution as shown in the first refractometry video. To ensure consistency, a total of 5 1 to 2 drop samples from each solution was analysed, using a clean pipette for each sample. After each measurement, the refractometer sample cell was cleaned. This table shows the ORI values as measured, as well as the average ORI for each solution and the associated standard deviation, which in all cases was of the order of 10 to the minus 5. Average ORI values are shown here, plotted on the y-axis as a function of ethanol mass fraction, shown on the x-axis. The error bars indicate the associated standard deviation. As ethanol concentration increases up to a value of about 0.3, ORI appears to increase linearly. For ethanol mass fractions of between about 0.3 and about 0.7, ORI is still increasing, but the relationship is no longer linear. For mass fractions above 0.8, the ORI falls slightly. Here, a second-order polynomial trendline has been fitted to the experimental data using Excel. The equation for the curve and the correlation coefficient are as indicated. This curve, which relates ORI to ethanol concentration, is called the calibration curve. The difficulty with this non-linear calibration curve is that a single value of ORI does not necessarily correspond to a unique ethanol concentration, but may relate to either one of two different ethanol mass fractions. For instance, if an ethanol water sample at 25 degrees C has an ORI value of 1.36, this could correspond to an ethanol mass fraction of either 0.51 or of 0.98, and it's not possible to know which is the correct value. Thus, this calibration curve cannot be used across the entire composition range. A second problem is that outside of the linear region, we have reduced sensitivity of ORI to changes in ethanol concentration. In other words, above the linear region, a change in ethanol concentration results in a proportionately smaller change in ORI. To address both of these problems, we will work only with the linear region of the calibration curve. And this is the source of the calibration curve introduced at the beginning of the video. The equation for the trend line and associated correlation coefficient are as shown here. Prior to analysis, ethanol water samples are diluted with water to ensure that they lie within the linear region of the calibration curve, in which any ORI value can be related to a unique ethanol mass fraction. By diluting the samples 1 to 4, for example, i.e. diluting 1 gram of ethanol water solution with 3 grams of water, all samples will fall within the concentration range corresponding to this linear calibration curve. Working in this way, remember that the measured ORI refers to the diluted sample. The ethanol mass fraction in this diluted sample is determined using the linear calibration curve. Multiplying this value by the dilution factor yields the ethanol mass fraction in the original sample. Thank you for your attention.